Today's lesson involves magnetic forces. So we're going to use as an equation force equals B, that's magnetic field strength, times I, electric current, times L, which is going to be the length of wire in the magnetic field. So in yesterday's digital lesson, we talked about a single wire, and if the single wire had a current running through it, we know that that would create a magnetic field. We used a hand rule, specifically a right-hand rule, which we call the hitchhiker rule, to determine the direction of that magnetic field. So we said the thumb would point in the direction of the current, which would be to the right, and then our fingers would wrap around the wire, and our notation was that they would come out of the screen above the wire and into the screen below the wire. Well, all that is a single magnetic field. There's no force yet on anything. For that to happen, we need a second magnetic field. So when we have two magnetic fields kind of competing with each other or perpendicular to each other, we have the conditions for a magnetic force. Or sometimes you'll hear it as an electromagnetic force, but it's a magnetic force. And here's an example below. So if we have a second wire going between two fixed magnetic fields. Now by fixed, we might as well show that these are like bolted to the table or something. So we have two fixed magnets here. And those magnets are going to have a magnetic field between them going from north to south. So we have a magnetic field between the magnets right where the wire is going. So the wire has current going up, but we know that the current causes a magnetic field around the wire. So I'll use a different color to indicate that, and it's really the same case as we just did above. It's just turned sideways, but my thumb is pointing up. So with my right hand, I would have the magnetic field coming out of the screen on the left side and into the screen on the right side. Now we're going to use a second right-hand rule, which I affectionately call the in-your-face disgrace hand rule. This is an open-faced hand rule, and it involves your fingers, thumb, and palm. So the fingers are going to show the direction of the fixed field lines. Lots of fingers, lots of field lines. Your thumb is going to be the direction of the current, so I'll say positive to negative, in other words, our convention, positive to negative flow of current. And then your palm, the palm is going to indicate the direction of the force. And to give a 3D representation of how to apply this hand rule, here is McQuaid physics teacher, Mr. Bix DeBaise. Thank you. I'd like to take this moment to show you the second right-hand rule, which is the in-your-face disgrace rule. And note that it's an open-faced rule and that my fingers are perpendicular to my thumb. My hand is flat. And using these macaroni and cheese boxes to represent the fixed magnetic field, my fingers are representing the field lines between going from north to south, the fixed magnetic field, and my thumb is representing the current. So I'm going to use the screwdriver to show the current. The screwdriver is pointed up, so this is representing a wire with current flowing straight up. When I do this, my thumb has to point straight up in the direction of the current. My fingers still have to point north to south. That fixes my hand in this position. That's the key, because the force is now going to come out of my palm and push on the wire in the direction towards the way you're looking. So it's becoming out of the screen towards you. And that's the key. So let's do an actual problem. Here we have a wire in a field, a straight wire containing a current of 5 amps. Okay, and it's directed up, so it's positive to negative. It's in a uniform magnetic field at right angles. That's important, although in regular physics we're only going to do the right angle case. When 0.1 meters of wire is in the field, okay, so this is important. It doesn't matter how long the wire is, it only matters how much of the wire, we'll use this green part, just this length of wire, just the amount that's in the field. It could be a mile long, and we're only going to use the length that's in the field to do this. So the force on the wire is 0.2, so they actually give us the force. So we're looking for the strength of the magnetic field. So our equation, once again, is F Bill. And if we want to just solve that for magnetic field algebraically, we'll just say B is force divided by I divided by L. Substituting, I'm just going to say 0.20 newtons divided by the current, which is 5.0 amps, and also divided by the length of the wire, which is 0.10 meters. This is just straight plug and chug, people. So my answer comes out to be 0.4 Newton amp meters, but a Newton per amp meter is a Tesla. Just to give you a little context of why this is important, suppose you had a metal bar, and coming out of the metal bar was a wire loop. Okay, and you simply ran current, so these have to be extended, but somewhere down here, one wire is connected to a positive terminal. This one's connected to a negative terminal. So we have current flowing through the wire in this manner. If we focus just for a moment on this branch here, and we were to apply the in-your-face disgrace right-hand rule, our fingers would go north to south. Our thumb would go in the direction the current is going, and the force, I use a different color for force, I use red. The force would go straight up on that part of the loop. But if you look at the left side of the loop, so if you look at this part of it right here, just the opposite would happen, and the force would be down on this side. That would have the effect of rotating the bar counterclockwise, and it would do that for half a rotation. And essentially what we're creating here is an electric motor. You would go half a rotation, and then to keep it rotating, you would then alternate the current. Okay, so when we say AC, or alternating current, we're talking about current that changes direction typically 60 times or 60 cycles per second. And essentially just by running current through that loop, you are spinning the motor at 30 revolutions per second. And then that could be geared up or down depending on what angular speed you needed.